The next question of lead code biweekly contest 120 is find polygon with the largest perimeter. So basically in this question, we are given some line segments. We can assume we are given some line segments with certain fixed length. So basically the line segments lengths are given in the form of an array. A1 is the first line segments, A2, A3, so on till A of k. So now we know the condition for a polygon, right? It's already given in the question as well. For a polygon, basically polygon is a closed figure. So for a particular figure to be a polygon, it should hold the following conditions. Let's say the polygon has sides. The polygon has n number of sides. Then the length of the first line segment, let me call it as L1. Line segment is first line segment is L1, then L2, then L3, L4, so on till Ln. These are the given sides of the polygon. So now among this, there should exist one line, one of the side, assuming that all these sides are in increasing order, let's say. Then for the following figure to be a polygon, it should hold that the largest side should be smaller than or equal to, should be smaller than, not equal, should be smaller than, so on till Ln minus 1. So the largest side should be smaller than the lengths, sum of lengths of all other sides. Then we say it's a polygon, and obviously there should be at least three sides for a polygon, because with two sides it's impossible to construct a polygon. So n should be greater than or equal to 3. Then we say the following figure is a polygon. So now what we have to do is, we are given some set of line segments with certain lengths. So we can choose from this given set of line segments, we can choose any number of line segments, and we should construct polygon. So among all possible polygons that we can construct, we should say what is the largest perimeter of such a polygon. So we should output what is the largest perimeter of such a polygon. If in case we couldn't construct any polygon with the given line segments, then we should output -1. So should find out largest perimeter polygon that we can construct by picking some set of line segments among the given line segments. If that is if there is no polygon which is possible, then we should output -1. So let's look at the constraints of the question. So here the constraints are number of line segments given can be in the range 1 to 10 power 5, and the length of the length of given line segments can be in the range 1 to 10 power 9. So these all are per test case. So let's see how we can solve this problem. So we can basically fix the largest side. Basically, we can do something greedily here. We can fix the largest side. We can fix the largest side of the polygon, and we can find out if that largest side, if that is the largest side of the polygon, then what is the maximum perimeter that we can get. So to solve this, let's take an example which would be clear. So we know that because the ordering doesn't matter, the order in which we pick the lines doesn't matter. Only thing matters is in the set which all lines are picked, right? So for that, what we can do is we can sort all these lines based on their lengths, 5, 12, and 50. So now we can firstly observe the monotonicality. Let's say if a larger line, let's say by using a larger line, basically if this is my maximum, if this is the line segment which is maximum, line segment which is the maximum side of the polygon, then it's always optimal to include all these, because as per our condition of the polygon, we see that largest line segment should be smaller than the sum of all other line segments. So it is always beneficial to include all the smaller line segments into the polygon. Then the probability of the condition to meet will increase, right? Because that is the scenario. What we can do is we can fix the largest line segment at every point and find out if that can be the line segment. As soon as we get a line segment, we can just break it, because we are already doing it greedily. We are coming from right to left. So more the line segments we include, better will be the perimeter. Right? More the line segments, because here, if we observe, if 50 is the largest side of the polygon, then all these line segments will get included. Right? Now, similarly, if 12 is my line segment, 12 is the largest line segment in the polygon, then all these will get included. Right? So we can observe that whatever we include, uh, whatever we include in the smaller fixed line segment, those all are subset of the larger fixed line segment. Right? That means basically, if I fix this as my larger line segment, then all these will be including in our polygon. Now, if I fix 12, then we are including all these. Right? So ultimately, whatever we are including in 12 is a subset of all those that we are including in 50. So from this, we can see it's always optimal to find out the largest fixable line segment. So now let's see how we can do this. If I fix 50 as my largest line segment, then we just saw greedily that it is always better to include all the smaller elements. Then the probability of the given condition, given polygon condition to hold will be more. So let's see if 50 satisfies. 50 is greater than 1 plus 1 plus. If we sum up all these sides, we get 4, 7, 12, 24. This is 24, whereas 50 is greater than 20, greater than or equal to 24, right? That means this can't, these set of line segments can't form a polygon. Now, if I consider 12, now 50 is done. Now let's make decision on, let's see if 12 can be the largest line segment of any polygon. So if we look over, 12 is lesser than 2 plus 3 plus 5. So the value of this is, so even here, if we look over, this is not a valid scenario, right? Why? Because 12 is greater than or equal to the LHS is greater than or equal to the RHS, as this will sum up to 12 if we look over. So even 12, even by picking these line segments, we couldn't get a valid answer. We couldn't form a valid polygon. Now, if I include this, if I consider this as my largest line segment, then we include all these. So let's see if these set of line segments can form a polygon or not. So 5 is smaller than 2 plus 3 if you look at it. Right? That is the value of this is 7, whereas this is 5. So this is a valid arrangement. So we can greedily see that if we find our answer for a larger fixed line segment as the largest side of a polygon, then it's useless reducing the largest side of the polygon, because perimeter will reduce. Perimeter is directly proportional to largest side. According to the way we are doing, the proportionality holds like perimeter is directly proportional to the largest side, because in the way we are doing, we are including all the elements lesser than the largest side. So that means ultimately smaller the largest side is, perimeter is also decreasing. So that is why we can just break here, and the perimeter of this would be 7 plus 5, which is 12. So this way we can sort and greedily find out the largest polygon. And in case if the polygon isn't, if there is no ith point, which can be the largest side of the polygon, and which can, and after taking the set of line segments smaller than it and including it doesn't satisfy the condition, we can output -1. So basically we can, what we can do is we check for this. In case if 5 didn't satisfy, then we'll check for 3, then we'll check for 2. After 2 we can stop, because however length 1 and 2 uh, are not valid polygons. So this way we can solve the problem. This way we can readily solve the problem. So if we look over the time complexity for this is, we are just sorting the line segments. So sorting, assuming n is the length of the given line segments, it would cost us n log n to sort. Plus we are fixing each line segment and greedily finding out our answer. So for each fixed line segment, we'll do it in n. So here what we can do is, instead of for each fixed line segment, instead of recalculating the sum, we can maintain the prefix value, or we can just maintain a variable. We can just maintain the total sum variable, and as we are moving from right to left, we can reduce the current value's contribution. So at the end, we'll be left with this part when our I is over here. So that way also we can implement. So one way is use prefix array, and other way is just maintain a suffix, just maintain a total sum variable till ith point. As we are starting from right to left, we can basically we will be having the sum of this whole part, which is this. Now, when we are moving to 12, we can just remove this from the sum. So this way, if we do, we can guarantee that we'll have sum of this part only. So this way we can implement it in this way using a single variable. So ultimately, time complexity will be n log n plus n practically. So in terms of big O, we can say it is equivalent to big O of n log n. And space complexity, it depends on how we implement. We can implement it with a space of big O of n and big O of 1 as well. So this way we can solve it.